Hi students, let us continue the topic of flow through the pipes here. Okay, now I am going to discuss the concept of hydraulic energy line and the total energy line. Nothing but we can also call the total energy line as energy gradient line, total energy line or energy gradient line, and the next thing is nothing but the hydraulic gradient line here. So what is the difference between the hydraulic gradient line and the total energy line? Let me clear all these things. Okay, so whenever the liquid flows, for example, let us take a pipeline. Let's take a pipeline here. Whenever the liquid flows in the direction of the pipeline, whenever liquid flows in particular direction, okay, the velocity of the fluid will be always changing. That means the total energy of the fluid will be always changing here. That means the total energy from one section to another section will be always changing here. Now what I want to do is, throughout this pipeline, I want to calculate the energy levels from one point to another point. I want to draw a graph, something like that. Okay, I want to determine the energy at different points of the given pipeline. Okay, see, actually if it is made up of the constant, diameter, it is made up of the prismatic. It is a prismatic pipeline, for example. Then there will be no much loss. There is no possibility of much loss here. For example, this pipe is having some sudden enlargement, some sudden contraction, some entrance of the pipe, exit of the pipe. Then there will be some drastic change in the total energy from one point to another point in the given pipeline here. Okay, now I am going to discuss in detail regarding the two number of lines we have. So I am going for two number of lines. The first thing is the total energy line. Very important concept. Definitely you may get a bit from this concept. Total energy line is always called as TEL. Okay. So first of all, let me write what is meant by TE. The total energy of the fluid at any point in a flow is given as, it is defined as the pressure head plus kinetic head plus datum head, which is equal to P by rho g plus V square by 2g plus Z is the value here. This is called as the total energy, or the total head also we can say. The total head here, or the total energy also we can say here. Okay, so if you calculate the total energy at all the points in the given pipeline, and if you join the points of the energy levels from one point to another point, this gives the line which is called as the total energy line. Okay, total energy line is a line which joins all the corresponding energy points in a given pipeline here. I will give the examples for nothing to worry about that. Next thing is nothing but we have a second line which is called as HGL. The second line is called as hydraulic gradient line. It is called as the hydraulic gradient line here, HGL. Okay, and this total energy line is also called as, we have one more name which for the total energy line, which is also called as energy gradient line, and this is called as hydraulic gradient line here. Hydraulic gradient line is nothing but which plots the energy for only the values of pressure head and then datum head. Therefore, I can write this value as P by rho g plus I can write this value as H plus H. Therefore, this value is always equal to hydraulic gradient. This value is the value which is obtained by removing the kinetic head. Okay. Therefore, how we can define the hydraulic gradient line? Hydraulic gradient line is a line which joins the points along the given pipeline such that those points are the values of the hydraulic gradient. Hydraulic gradient is obtained by which is nothing but the pressure energy and then datum head here. That is the value, only value we can get here, datum head. This is called as the hydraulic gradient line. And we can say one thing, what is the difference between the total energy line and the hydraulic gradient line? What is the difference between these two lines here? If you observe, in this head we have totally 3 number of heads here. In this head we have only 2 number of heads. If you subtract these two, So what is the head we are left over with? Is nothing but the value v square by 2g. V square by 2g is the value which is left over. Okay. Therefore, at any point, if you observe the difference, definitely this difference between the lines, height of the lines will be equal to the velocity head here. The velocity head is always equal to kinetic energy per the unit weight of the liquid here. Okay. So we shall do a small problem. I will just draw the lines and I will come back and I will explain once again this concept for you clearly, because without figures you cannot get the concept. Just I am telling what is meant by total energy and gradient line. If you mark the, if you determine the total energy at different points in a given pipeline, okay, and if you join all the points in a given pipeline, okay, that line is called as a total energy line, or it is also called as the energy gradient line here. Okay. Now, the second case, if you determine the energy by omitting the velocity head, or by omitting the kinetic energy, if you determine the total head by omitting the kinetic head, so the remaining head will be equal to pressure head and the datum head. So if you determine the sum of the pressure head and datum head, all the points in a given pipeline, and if you join all these points here, that line is called as the hydraulic gradient line here. If you get the difference between these two, this difference is called as the kinetic head here. Okay. And one more thing is, the hydraulic gradient line will be always lying below the total energy line here, or the hydraulic or the energy gradient line. This line will be always above this line, or this line will be always below this line here. Okay. Now I am having some points to discuss with you. The sum of the potential head and the pressure head at any point is called as piezometric head. So this is called as a piezometric head here. Piezometric head. Piezometric head is always defined as the sum of the pressure head and the datum head. Okay. So if you determine all the piezometric heads at different sections of the pipeline, and if you join the line, that line is called as a hydraulic gradient line here, he was saying. Okay. So if a line is drawn by joining the piezometric levels of the various points, the line so obtained is called as a hydraulic gradient line here. Energy will be, even though you have the constant diameter or varying diameter toward the entire pipeline, there will be some loss of energy in the direction of flow. In the direction of flow, always there will be some loss of energy. We have done some problems in the Bernoulli's equation, right? Now, for example, I am taking a nozzle here. Nozzle in the sense I am taking a converging section. This is section 1, this is section 2 here. For example, I want to know whether the flow is in this direction or whether the flow is in this direction. I want to know this nozzle is having flow from section 2 to 1 or from section 1 to 2. I want to know the direction of flow. So what we have done? Is, for example, we have determined the total energy at section 1, and also we have determined the total energy or the total head at section 2. Okay. For example, after determination of section total energy, if the TE1, if the total energy at section 2 is greater than total energy at section 2, for example, if this value is greater than this value, therefore what we can say is, so this energy is greater than this section. Okay, that means in this direction the energy is reduced here. Therefore what we can say is, the flow is moving from section 1 to section 2 here. Even though if we move for 1 meter of length, in the direction of flow, definitely there will be some loss of energy here in the direction of flow here, right? Okay. In the same way, for example, after determining these values, the total head of section 2 is greater than the total head of section 1, for example. Then what we can say? What we can say is the total energy at section 2 is greater than total energy at section 2. Therefore, what we can say is the flow is moving from section 2 to section 1. It is having the flow in this direction, we can say here. So depending upon the value of total energy here, we can determine the direction of flow. Okay. So if you have the friction laws here, you can include the friction laws. If the values are not given for us, no need to go for the inclusion of those values here. Okay. Right. Okay. Now we have some conclusions for this one. So before going to the conclusions, I want to go for a simple example for you in that case. Now see here. Please try to note down all these things. So it is kinetic head here. You can write this one as total head. No problem. Total head is equal to pressure energy plus kinetic, write as kinetic head only, sorry, kinetic head plus datum head I can write, the values we have. Okay. So let me go for a simple example, then you can go for the concept here. The two number of tanks we have. I am going for a simple example for the clear understanding purpose of this two number of lines here, between two number of lines here. This is the level of the water we have. Okay, and this is the tank I am drawing here. The simple example I am going for. This is the pipeline. So at this pipeline we have a sudden enlargement which is connected to one more pipe, or it may leave the water freely into the tank here, which is freely left into the atmosphere here. Okay, so this is the position of the pipeline here. Now if you observe carefully, this is the level of the water level. This is the level of the water in the tank here. So this is the entire height of the water level in the tank. Okay, now whenever the liquid enters into this pipeline, certain amount of energy will be lost as the energy due to the sudden entry or at the entry of the pipeline. As I told, the energy due to the entry of the pipeline is always equal to 0.5 into V square by 2G is the value. This is a very important formula here. 0.5 into V square by 2G is the head loss due to the entry of the pipeline or at the position of the entry here. Okay, so actually first of all, let me see the energy positions. So this is the point here. Next, this is the I'm having totally three number of sections here. The first section is due to the entry we have a loss, and next thing is due to friction along this line L1. This is the line L2. Due to friction we have some loss here, and that loss of energy due to friction is equal to, I am writing 4F L V square by 2 into Z into D is the value here. Okay, and here at the end of this, the first pipe, let it be some L1 is L2. At the end of this length L1, we have the sudden enlargement. Due to enlargement, we will be having the loss of energy. So that loss of energy due to enlargement, as I told in the first case, we have the sudden enlargement. The value is equal to some V1 minus V2 whole square divided by 2G is the value here. That is the value. So one more thing is we will be having the loss of energy at the exit of the pipeline. Okay, so therefore I can write the value of HE is equal to loss of energy at the exit. This is the exit level here. At this exit the value is equal to, simply I can write this one as V square by 2G. Okay, now I will tell once again. So this is the starting position of the liquid. it is the point where the liquid enters into the pipeline. This is a total pipeline here. And this total pipeline is having two sections, having a length L1 and having a length L2 here. And this length L1 is having a diameter of D1, it is having a diameter of D2. The velocity of the fluid flowing in the length L1 is V1. The diameter of the fluid flowing in the length L2 is nothing but V2 I can have. Okay. So therefore, the loss of head in the section in the length L1 is HF1. The loss of head in the pipe L2 is equal to, in the pipe L2 is equal to HF2 I can write here. It is called a HF1, that is equal to HF2. HF1, HF2 as I wrote here. I will write values. So it is the value D2 comma V2 here. Okay. Now I want to calculate the total loss that is incurred in the pipeline. Therefore I can write the total loss is equal to, I am starting from this position here. At this position we have a certain entry. Okay. Therefore I can write this value as 0.5 into V square by 2G. And from this position to this position, this pipe, we don't have the change in diameter. So due to the friction you may have some loss of energy. Therefore I can write this value as 4 F1 L1 V1 square by 2 into G into D1. At the end of the first pipe, at the end of the line L1 we have a certain enlargement. Therefore I can write this value as V1 minus V2 whole square by 2G plus, so the loss of energy at the exit, I can write this value as V square by 2 into G is the value. Is the value here. This is the total loss of energy here. Okay. And now what I want to do is I want to draw the total energy line and the hydraulic gradient line for this pipeline. Okay. Now see here, I am just removing this surface here. I am going to draw the total energy and hydraulic gradient line for this pipeline, for this entire pipeline here. I am going to show, you can start with any point here. You can start with any point here. I am just starting with this point here. Okay. So at this point, if you observe carefully, at this point, I am starting with this point. At this point, this is the starting point. It will be some point A I am taking here. This is the starting point here. So at this point only, we have some loss of energy due to the entrance of the liquid into the pipeline. Therefore, the total energy will be reduced to some extent. It will be reduced here. And it will come to the point B here. It will come to the point B. So AB is nothing but loss of energy due to the entry into the pipeline here. Okay. So next. So while coming from this point to this point here, this is the loss of energy due to the friction. Therefore, the line will be an inclined line here. You will be getting this point here. Okay, I am taking this point as some point C. First of all, you can draw the line directly. You can first of all mark the points also. What is there in that? Okay. Next. So at this point, after coming to this point here, since we have certain enlargement here, there will be some loss of energy here. Therefore, the point C will fall down. Okay, to the point D here. Okay. So next what will be happening is along this entire length we will be having some friction. Therefore this line will be an inclined line here. Okay. Therefore I am taking this point as some point E. This point E here. Okay. So these values A, B, C, D, E, all these points are the values of total energy. Total energy in the sense it is the energy per unit weight, or it is the total heads. All these points are total heads at the corresponding sections. The total head is nothing but pressure head, datum head, and then kinetic head we have. So if you add all the three number of heads, you'll be getting this value here. It's nothing but the point E. Okay. Next. Now this total line is called as the total energy line, or it is called as the energy gradient line here. Okay, now it is a thing here. Now what I want to do is I want to draw the hydraulic gradient line. So how we can get the hydraulic gradient line? Hydraulic gradient line is the line which is obtained by removing the velocity head. It is the line which is obtained by removing the velocity head here. So how we can determine the velocity head here? Okay. Now see, I am drawing the velocity head for you. Very important point I want to say. See here, for example here, so due to the thing here, I am starting with this position. I am starting with this position here. So this point, some point, let it be some point P here. So P is the energy at this position. So due to the pressure, due to the loss of energy due to friction, so you will be having the line, you will be getting a line that is parallel here. Okay, and I am joining this line to this position here, and whenever this pressure is increased, I mean whenever this area is increased here, what about the velocity? Velocity will be generally decreased. Whenever the area is increased, velocity will be decreased, but pressure will be increased. Pressure will be increased here. Since the pressure is increased, there is a rise in the line of this. Now the rise in the height of this line here. Now this is the line here. So it is some point Q, it is a point PQ, it is a point R here. Okay. And now due to the pressure, due to the viscosity or the friction here, again the line comes down, and this is the position of the line here, and there is nothing but the point S here. That is the thing. Okay. And if you remove this pipeline, for example, just I want to conclude these two things here. This is the point S I am going to say, I want to mark here. So if you observe these two lines here, so this is the line A, B, C, D, E. This total line represents the total energy or the gradient total or the height or the energy gradient line we have. And next thing is, this is the line, you can see this line is called as the hydraulic gradient line. This line is called as the hydraulic gradient line, which is obtained by removing the velocity. Okay. And if you observe carefully, here we will be losing the energy. We will be losing the energy here. So energy is loosed means, which type of energy is loosed here? Actually at the entrance we have the value of 0.5 v square by 2. That means the velocity is reduced here. The velocity head is reduced. But actually this is the line which is obtained by joining the piezometric heads. This line does not include the velocity heads. If there is an increase in the pressure, we have to show this pressure. If there is a decrease in the pressure, we have to show that pressure. That's all. Okay. So due to the increase in the pressure here, okay, due to the decrease in the velocity here, increase in the velocity, the pressure is decreased here. You can observe this one. It becomes the point B here. Therefore, P, Q, R, S. Therefore, this line represents the hydraulic gradient line here. And if you observe the difference between these two lines at any point, if you observe the difference between this difference gives always the value of the kinetic head, which is always equal to v square by 2g. That is value which is always equal to, kinetic head is always equal to v square by 2g, or the kinetic energy per unit weight also I can say. Okay. Now from these two lines I want to tell some conclusions for you. So by using this conclusion you can understand clearly. Now see here. So yeah, see here. The first points that we have to observe from the energy gradient line and the hydraulic gradient line. The first point is, energy gradient line always drops in the direction of the flow because of the loss of head. If you observe carefully, the line is inclined towards down. If you observe this line, the line is inclined. This is the line here I am drawing for this is the line I am drawing for the total energy line here. So inclined line, again drop, again inclined line. If you observe carefully, this is dropping. This is the initial position, this is the final position here, right? So these are the total energy lost, I can say. Total energy lost, I can say. This total energy lost here. Okay. This total energy lost is due to many number of reasons. Therefore, what we can say, since it is a direction of flow here, in the direction of flow, always the total energy line drops down. That is the conclusion. Okay. Next, second point. Hydraulic gradient line may rise or fall depending upon the pressure changes. The total energy line always drops down, but the hydraulic gradient line may rise or fall, because hydraulic gradient line always involves the value of pressure head. So pressure head plus datum head. If there is increase in the pressure, the hydraulic gradient line will rise. If there is decrease in the pressure, the hydraulic gradient line will come down. Okay. So it depends upon the value of the pressure. So if the diameter of the pipe is increased, means what happens? The pressure will be increased. If the diameter of the pressure is decreased, if the diameter of the pipeline is decreased, means the pressure will be changing. So therefore, depending upon the value of the diameter of the pipeline, the pressure value will be changing here. Depending upon the value of the pressure value at all the points, the position of the rise or lift of the total hydraulic gradient line will be reduced here. Okay? Okay, the hydraulic gradient line may rise or fall depending upon the pressure changes. Third one, hydraulic gradient line always lies below the energy gradient line, and the vertical intercept between the two is equal to the velocity head, as I told. Okay, you can see we have two number of lines here. This is the line number 1, this is the line number 2 here. So it is line number 1, it is line number 2 here, right? So these two lines, if you observe carefully, these called as the hydraulic gradient. This hydraulic gradient line lies always below the total energy line, and the difference, the vertical intercept, these called as vertical intercept. It means vertical height or the vertical distance or the vertical gap between these two lines is always equal to the velocity head, or it is always equal to kinetic energy per unit weight. Always defined as the kinetic energy per unit weight. Okay. And next difference. For a pipe of uniform cross section, the slope of hydraulic gradient line is equal to slope of energy gradient line here. Okay, for a pipe of uniform cross section, let us see. For example, I am taking a uniform cross section pipeline. Okay, now if you observe carefully, so it is the energy line I am drawing here. So the energy is reduced because due to friction. Okay, in the same way we will be having the hydraulic gradient line. It also remains constant. Okay, therefore the slopes will be parallel, the slopes will be equal. So there is the inclined line here which is having some slope, and there is the inclined line which is having some slope here. So for these two inclined line slopes will be equal. That means these two lines will be parallel to each other. If the pipe is made up of same diameter, these two lines will be parallel to each other, having the same slopes. Same slopes in the sense parallel to each other, that's all. Okay, so try to write some points from the conclusions. Okay. Yes, let us do a small problem in case of the pipes here. Okay. Now see here, what he was saying is, a horizontal pipeline of 40 meter long is connected to water tank at one end and discharges freely into the atmosphere at the other end. For the first 25 meters of its length from the tank, the pipe is 150 mm diameter. So the length of the first part is equal to 25 meters, and for that length L1, the diameter is equal to 150 mm, I can say. And its diameter is suddenly enlarged to 300 mm. That means we can say this pipe is having sudden enlargement. Loss of energy due to enlargement we have to write. The height of the water level in the tank is 8 meters above the center of the pipe. Okay, the height of the water, the height of the water level in the tank is 8 meters above the center of the pipe, considering all losses of the head which occur. Okay, determine the rate of flow and represent the hydraulic gradient line and the energy gradient line here. First of all, let me draw the figure, then I will explain the question once again, and I will just tell what we have determined from this problem. We have determined the total rate of flow. So rate of flow can be obtained by the corresponding area and the velocity. If you determine the velocity, then you can determine everything here. Okay? I am drawing the figure for you. I am reducing the diameter here for you. Okay, it is having a diameter D1, length L1, it is having a diameter D2 and then length L2, it is having a velocity V1 and it is having a velocity V2 here. Velocity V2, it is having a length L2, it is having a D2 here. Okay. Now how we can determine the rate of flow here? So first of all, let me write the given data for us. Okay, there is a tank here, and this tank is having a free water surface level. Okay, and the level of the tank is equal to 8 meters I am having. It's level of the water level. Okay, this is the entire water we can have in the given pipe, in the given tank. Okay, and the distance from the axis of the pipeline to the free water surface level, it is called as a free water surface level, which is exposed to the atmosphere. So at the surface, the atmosphere pressure will be always acting. First of all, let me write the given data. So what you were saying is the length L1 is equal to 25 meters. Okay, the diameters, atmosphere for the first 25 meters from the tank, the pipe is 150 mm diameter. Okay, and its diameter suddenly enlarged to 300 mm. I am taking this diameter equal to 300 mm here. Okay, the height of the water. So what about the length L2? So length L2 is not given for us. 1 minute. Yes, total length is given. The total length of the line is equal to 40 mm. Therefore, I can write this length L2 is equal to 15 meters I can get. Okay, very good. Okay, so see, this is the length L1 here, the section L1, and this is the length L2 here, length of the second section I can say. So length L1 and L2 here we have. So what we have to do? We have to calculate the total discharge. How we can calculate the total discharge here? First of all, let us write the Bernoulli's equation for this one. Bernoulli's equation. Therefore, I am writing the Bernoulli's equation. So I am applying the Bernoulli's equation between two sections. The first section is the section 1-1 at the topmost position of the tank, and this is the section 2-2 here at the extreme section of the pipeline. At the end of the pipe, at the exit of the pipeline, I am taking the section 2 here. Section 1 and section 2. It is section 1 here and section 2 it is. Okay. I am applying the Bernoulli's equation between section 1 and section 2. Therefore, the value will be equal to P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus head losses. I am writing this value as head losses here. Okay. So, what are the different head losses here I can write? See here. So, starting from the entry to the exit, there is the entry and there is the exit here. There is the entry and there is the exit here. What are the losses we have enclosed here? See, we will be having the loss of energy due to entry, as I told. And next thing is nothing but loss of head due to friction in the length L1. Next we have a certain enlargement. So loss of loss of head or the energy due to the certain enlargement plus loss of energy or loss of head due to the friction that is present in the length L2. And at the exit you will be having some more loss. Okay. So 1 plus 2 friction, 3 sudden enlargement, 4 is nothing but again friction, and 50 is nothing but again exit we can write. Therefore I am writing all the losses here. So due to entry HI I am representing here. Next due to the pipeline HF1. Next sudden enlargement HE. So due to the friction in the pipe 2 plus exit. Therefore I can write this value as EXIT. This is a total statement we have to calculate. Okay. Now we will be calculating these values later. Now see here. This is the head loss. Head loss, HL it is. So can we minimize any terms here? Let us see. So P1 by rho g stands for pressure head at this position. At this position, atmospheric pressure is acting on the surface of the tank. So therefore, can I take this value as atmospheric pressure head? Yes, we can take this one atmospheric pressure head here. So what is the pressure at this exit? I am taking exit as section 2 here. Therefore, what is the value we can get? Okay, therefore this value will be always equal to the atmospheric pressure head or the atmospheric pressure that is acting here. Okay, next, what is the velocity V1 at this surface? This liquid is at rest. Okay, therefore I can take the velocity. I can take the velocity V1. I can take the velocity V1 is equal to 0 here, because this value is equal to 0. The liquid is leaving with rest. I can take this value is equal to 0 here. So Z1. So what is the distance of this section 1 from the datum line? I am taking the axis of the pipeline as a datum line. This is the datum line I am taking. Let it be some datum line XX I am taking here. So from the datum line to the topmost surface, what is the height value which is equal to Z1 I am taking. Therefore, can I write the value of Z1 is equal to 8 meters. Therefore, if you cancel these two terms, this value is equal to 0. You will be left with only the value of Z1 is equal to velocity. Velocity at section 2, you will be having some velocity here. Don't keep this velocity V2 0, because the liquid comes out with some velocity into the atmosphere. If the velocity at this section is 0 means the valve should be closed here. You will be having some valve now. If the valve is closed means the velocity will be equal to 0. If the valve is open means you will be having some velocity. Okay. Therefore this velocity will be existing. This value will be equal to V2 square by 2G. What about Z2? Z2 is the distance from the section 2 from the datum line. Section 2 from the datum line. Yes, the section 2 and the datum line are at the same position. We don't have any distance. Therefore, I can write this value is equal to 0 plus head losses. Okay. Now substitute the value of, determine the value of head loss here and substitute the value of head loss here. Okay. What is the value of Z1 is equal? Z1 is equal, I can write this value as 8, which is equal to V2 square by 2G plus HL. Okay. So how we can determine the value of HL? Let us see. So HL is equal to, I am writing this value for entry. Entry we know the value which is equal to 0.5 V2 square by 2G. Why we are writing V1? Nothing but see, V is the entry to this pipe of length L1. Okay, the velocity of the liquid that is flowing in the pipeline is having a velocity of V1 it is having. Therefore I can write this value as 0.5 into V1 square by 2G plus, therefore I can write 4 F1 L1 V1 square divided by 2 into Z into D1 plus what about the value of enlargement? Due to sudden enlargement, what is the value we have? I can write this value is equal to, so V1, before enlargement the value is D1, after enlargement the value is equal to D2. Therefore I can write this value as V1 minus V2. So I can write this value as V1 minus V2 whole square divided by 2G plus what is the value of head loss? Therefore I can write this value of head loss is equal to 4 into L2 into V2 square by 2 into G2 into D2, G into D2 plus what is the head loss due to exit? At the exit what is the head loss? As I told, it is V square by 2G. So the velocity with which it is leaving the pipeline, I can write this value as V2 square by 2G. Therefore I can write simply it as V2 square by 2G is the relation we can get. V2 square by 2G. Okay. Now, to get this value of HL, we need the values of F1 and F2. So what about the friction factors? Yes, he is given that friction factor is equal to 0.01. So for all the pipelines, so F1 is equal to F2 is equal to F is equal to 0.01. He was saying this is the pipeline friction coefficient, or the coefficient of friction value is given for us. So F values are known to us, L1, L2 are known to us, HL should be determined, D1, D2 is known to us. But what about the values of V1 and V2? Any discharge value is given, no discharge, it should be determined. So what we have to do? We have one relation, nothing but, so the flow is constant from the law of continuity equation. Therefore I can write A1 V1 is equal to A2 V2 here. Therefore I can write pi by 4 into D1 square into V1 is equal to pi by 4 into D2 square into V2. I am substituting the values here. Pi by 4 into, what is the value of D1? 0.15 whole square. So what is the value of V1 is equal to, should be determined. Okay, so pi by 4 into, what is the value? D2 stands for 0.3 whole square into the value how much? V2. So you can get the relationship between V1 and V2. The value is equal to, V1 is equal to 4 into V2 is the value we can get. This relation. Now substitute the value of V1 in terms of 4V2, and I am writing the value. V1 is equal to 4V2. You can see here, I am removing this V1 and I am writing the value of 4V2 whole square, and I can write this value as 4 into V2 whole square. I am just substituting here. So V1 is nothing but 4V1. V1 is nothing but 4V2. 4V2 minus V2 is equal to 3V2. Therefore I can write this value as 3V2 whole square is equal to 9 into V square divided by 2G plus this value loss of Vt. So if you substitute all the values, the value of G, the value of diameter, the value of length and the value of F2, F1 and F2, then you can determine the value of V2. The final value of this V2 from this relation, from the entire relation, the value of V2 is equal to, I will tell the value for you. Okay, the value of Vt is equal to 1.11 meters per second is the value. 1.11 meters per second is the value. This is a very important value. You have to do all the calculations to determine this value V2 here. Okay, and we need to calculate the values of the loss of head due to the friction. Calculate loss of head due to all the loss of head due to everything, every changes in the diameter. That means every change in the exit and entry, all the things we have calculated, and we have determined the discharge. That is the main question for us. Discharge is equal to, I can write this value, discharge is equal to A2 into V2, pi by 4 into diameter D2 square. D2 is equal to how much I can write? I can write this value as 0.3 whole square into V2. What is the value of V2 stands for? V2 is equal to 1.11, I can say. This is the value of Q. So therefore I can write the value of Q is equal to, discharge is equal to 0.078 meter cube per second is the value here. That is the value of the discharge. Okay. So already for this figure we have seen the total energy line or the energy gradient line, and the hydraulic gradient line also we have seen. Okay, this is the way how we can represent all the losses in the given pipeline. All these are the losses here in the given pipeline. Okay, just please note down. Okay. Let us go for the next concept. Very important concept. Okay, so I'm going for the next topic, which is called as pipes in series and compound pipe. So how we can define the compound pipe here? So I want to go for a simple example for you to determine to give the difference of a compound pipe. See here, for example, now I'm just taking a pipeline which is having the changes in the diameters. The thing here. So this is the pipeline. This is a pipeline which is having different sections. Nothing but which is having different diameters here, connected one end to the other end with the length of L1, V1. Next, we can say this one as some loss of friction. I can say this one as HF1. Next, L2, V2, diameter D2, and take this one as diameter D1, and this is nothing but L3, V3, diameter D3 it is. These are the values for different sections here. Okay. The only concept in this relation is nothing but in all these sections, in the pipe 1, in pipe 2 and pipe 3 here, the only thing is the discharge will be remaining constant. We can say that the discharge in all the pipelines is equal. We can say the discharge in all the pipelines is equal. According to law of conservation of mass, and mass can be created, not destroyed. The mass cannot change from one position to another position here. So if you connect some more pipes of with some different diameters, okay, the discharge in all the pipe sections will be same. By using this condition only, we will be calculating the unknowns. By using this condition only, we will be calculating the unknowns. What is meant by compound pipe? Compound pipe is a pipe which is having different pipe lengths of different diameters, connected with each other from one end to the other end. Okay, therefore I can say this one as the compound pipe here. Very important pipe it is. Okay, so the very important point that you have to remember is, in this compound pipe, at every section in this pipe, the discharge will be always remaining constant here. So these regarding the pipe in series and compound pipe here. Now I want to go for a simple example, then you can understand clearly here. Okay, I will just draw a small figure for it, then you can understand clearly. I am taking two reservoirs. Okay, in between these two reservoirs, I will just fix a compound pipe. Okay. Levels of the pipe. tank container, this is a level here, this is one more level here. So I am just extending these lines here, and difference between these two levels is equal to, I am taking this value as H. Okay, so this is the reservoir A and this is the reservoir B here. Okay, or the tanks also we can say. Tank is nothing but reservoir used for the storage of water. So between these two reservoirs I am just using a tank, I am just using a compound pipe here, which is having different diameters and different lengths here. This is having a length of L1 comma diameter D1, length L2 comma diameter D2 I can say. Length L2 comma diameter D2, and it is having length L3 comma diameter D3 here. Okay, so these are the lengths we have connected with each other. So the flow takes place in this direction from one reservoir to the another reservoir. Now what we have to do here? We have to determine the height between two reservoirs. I want to determine the height between two reservoirs. It is the first question. Or if this height is given to you, we have to calculate the value of discharge in the given pipeline. We may have two questions. The first question is, if height is given to you, we have to calculate the discharge. Second question is, the second model will be, if discharge is given to you, we have to calculate the value of height. Okay, the problem is very simple. We have to apply the Bernoulli's equation between two surfaces. Now see here. See, actually, if there is flow inside the pipeline here, the level of the tank A will be decreased, and the level of the tank B will be increased here, right? It will be decreased, it will be increased here. Okay, but the value of H will be remaining constant. The value of H may not change, because if there is any decrease in the value of level of the tank, at the position A, okay, the same amount of decrease will be equal to the same amount of increase of the level in the tank B here. Whatever the level that is reduced will be equal to whatever the level that is increased here. Okay, and this is the total water level I am taking. Okay. Right. Now I want to apply the Bernoulli's equation between the section 1. I am taking this section as 1, and I am taking this section as 2 here, between two number of things here. Two sections I am taking here between level 1 and level 2 here. So how we can determine how we can apply the Bernoulli's equation? I am applying the Bernoulli's equation between these two. So P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus head loss I can say. Okay. So what is the pressure acting at this surface? Is always equal to the atmospheric pressure I can say. Atmospheric pressure is acting. At this surface also atmospheric pressure is acting I can say. Okay. Therefore I can write this value as P is equal to atmospheric pressure head, and this value will be also equal to atmospheric pressure head. Oh, the velocity will be equal to 0. The velocity equal to 0 at these two positions. At the topmost position, the free surface of the water, the velocity is equal to 0 here. Therefore, the terms which will be left over will be equal to Z1 is equal to Z2 plus HL we can say. Okay. Now I am writing the value of HL is equal to Z1 minus Z2 I can write. So I am taking the reference level. Where we should take the reference level here? Let us take the datum level at this position. I am taking this one as the datum level XX for example. It is the datum level XX here. Distance from the datum level to the topmost level is equal to H I can write. Therefore I can write the value as Z1 minus Z2 is equal to H I can write. Total height. Therefore the very important relationship we can get is the total head losses in the given pipeline is equal to height H, and this is the height between the two reservoirs. Very important conclusion I am saying. So no need to do all these things in the examination. We have to know the concept, how this thing came is nothing but this thing came from the Bernoulli's equation only. The very important conclusion is the whatever the height that is present between the two reservoirs, this is a reservoir level here. Whatever the height that is present between the two reservoirs, this height will be always equal to the total loss in the compound pipe here. Total loss in the compound pipe is equal to total loss in the compound pipe here. Okay. So therefore, I can write this value of the compound pipe as, and the head loss I am writing here. So head losses, what are the head losses we can get? Head loss is equal to certain entry we have. So HI I can write, therefore I can write this one as HF1 due to friction plus contraction. See, here we have a contraction. Here we have a entrance. Here we have contraction C. Again we have enlargement here in this case. And here we have exit. Okay. Now if you observe carefully, see here HF1 plus here we have contraction. Contraction, it is a velocity V1, it is a velocity V2, it is a velocity how much? V3 I can write. Okay. So in the contraction, what is the value? The value will be equal to V2 square divided by 2G plus loss of head in the second pipe HF2 plus, so what is the thing we have? We have certain enlargement. Therefore I can write this value as certain enlargement. So this velocity will be reduced. Therefore I can write V2 minus V3 divided by 2G whole square. Even if you reverse these values, the value will be square. The value will become positive. Nothing to worry about that. So plus I can write this value as HF3. There is value HF3 here. So HF3 plus we have one more loss which is called as loss of head at the exit. I am writing this value loss of head at the exit, and this value is equal to V3 square divided by 2G. There is a value here. This is the loss of head in this total compound pipe. Okay, we can see the differences. So how many losses we have? So entrance plus friction plus contraction plus friction plus enlargement plus friction plus exit. So 1 plus 2, 3, 4, 5, 6, 7 number of losses we have. So we have to count all the losses, and this total 7 number of losses, the value which is obtained by adding all these losses is equal to the difference of height between the reservoirs. Difference of height between the reservoirs here. Okay, you may have an inclined pipe in this way also. Okay, you may have in any position. So please note down. Okay. So one more thing is, so it is the value, this is the value of H. The value of H, which is nothing but difference between the levels of the reservoir, which is equal to the major losses, I can say, plus I can write this one as minor losses. Okay. Sometimes he will be asking us to calculate the value of discharge by considering the major losses only, or he will be telling that neglect the minor losses and calculate the value of discharge he will be asking. Okay. So in those cases we should be able to omit this value, and we have to keep this value neglected, or we have to keep this value as 0 here. Therefore in those cases, so the value of H will be equal to, so simply HF1 plus the value is equal to HF2 plus the value is equal to HF3 here. So this is the sum of the frictional, the losses due to the frictional forces acting on this body here. Okay. So if you have two lengths of different diameters, then you can go for HF1 and HF2. If you have different diameters, you can get the value of HF2 and HF3 here. Okay. So depending upon the consideration, he may ask us to determine the discharge by considering the minor losses or without considering the minor losses. By negating the minor loss also he will be telling. So just read the question carefully and apply the equation you can get. The main conclusion is, if two reservoirs, these are reservoir 1, reservoir 2 here, if these two reservoirs are connected with the help of a pipeline, okay, and this pipeline can be a compound pipe. Compound pipe is something but the pipes in series. Okay, series in the sense the different pipelines are connected with end to end with different diameters. Okay, or these two reservoirs may connect with the help of a pipes in parallel connection. So I will be telling those things also for you. So if it is the case, we have to go for the total loss of it is always equal difference between the levels of the reservoir. It is constant. Okay, right. Okay, let us do a small problem by just considering the losses and without considering losses here. So what he was saying is, we have 3 pipes of diameter. 3 pipes of diameter 300 mm, 200 mm and 400 mm, and length 450 mm, 255 mm and 350 mm respectively. The difference in water surface levels in 2 tanks is equal to 18 mm. Determine the discharge. The coefficient of friction for the pipe 1 is 0.0075, pipe 2 is 0.0078 and the pipe 3 is 0.0072. Determine the value of discharge by considering the minor losses, by neglecting the minor losses. By considering minor, neglecting the minor losses. Okay. Now first of all, let me draw the figure, a small figure. The diameter is reduced. Okay. Okay, and then again the diameter is increased here up to the 400 value. Okay, and here we have a tank, reservoir we have. So no problem, nothing to worry about the reservoir. We'll just reduce the diameter for you for clear. Some of them may not see the view here. Okay, it's a pipeline. Okay, the difference between the levels of the reservoir, I can take this level of the reservoir is equal to H, and this value is given as H is equal to, this value is given as H is equal to, 1 minute. And the surface, the levels of the difference between the surface is equal to 80 meters it is given. It is having a length L1, L2, it is L3 here. Okay. So therefore I am writing the lengths for you. First of all, L1 is equal to 450 mm. L2 is equal to 255 mm. Okay. L3 is equal to 315 mm. And I am writing the diameters for you. D1 is equal to 300 mm. D2 is equal to 200 mm. And what about D3 I am writing? D3 is equal to 400 mm I am writing. Okay. So we have to calculate the discharge. This is the question we have to determine. So this is the term we have determined. Discharge is to be determined here. Discharge is to be determined here. So the first thing is we have to determine the discharge by including the minor losses. So one more value is given for us. The frictional force value is given for us. So F1 is equal to 0.0075. Okay. And the value of F2 is equal to 0.0078. Next, F3 is equal to 0.0072 is the value. That is the thing. 0.007 is the value. Okay. Now how we can calculate the value of the total head velocity? See, discharge can be calculated by knowing any one of the velocity of the liquid in the pipeline. You can write A1 V1 is equal to A2 V2 is equal to A3 into V3. Therefore, since we have three number of pipelines here, three number of pipes we have here in the velocities V1, V2, V3. So how we can determine the values of V1, V2, V3, D1, D2, D3 values are known. If any velocity value is known to you, if even one velocity value is known to us, after substituting the value of velocity, you can determine the value of discharge. So how we can determine the value of velocity here? So in the direction of the flow here, I am taking this value as V1. The direction of velocity, I am taking this value as V2 here. And I am taking this velocity as V3 here. Right? V1, V2 and then V3. Okay. So how we can determine the discharge here? I am just writing the Bernoulli's equation, applying the Bernoulli's equation between two free surface water levels from tank 1 to tank 2. Okay, from tank 1 to tank 2, applying the Bernoulli's equation here. Therefore, I can write this value as P1 by rho g plus V1 square by 2g. So no need to write all these things, I am writing the step directly. Okay, so P1, V1, P2, V2, all things will be, P1, P2 will be cancelled, V1, V2 will be equal to 0. So Z1 minus Z2 will be equal to height h I am writing. Okay, therefore I can write this value as height h is equal to, so it is entry, okay, it is contraction, it is enlargement, again it is nothing but exit here. So 1, 2, 3, 4 are the minor losses, plus friction 1, friction 2, friction 3 are the major losses. So we have 3 major losses and 4 number of minor losses. Totally we have 7 number of losses in this compound pipe. So in the first step, we have to include all the 7 number of losses and we have to determine the value of discharge Q. Okay. So therefore we can get the value of V1 or V2 or then we can go for the relations here. Right. Now I am writing the value of H1. So at the entry, the value will be always equal to 0.5 into V1 square by 2G. Okay. So 0.5 into V1 square divided by 2G plus, what about this value? Okay. So what about this one? I can write this one as HF1 plus, what about this contraction? This contraction. So how we can reduce the contraction here? By not reducing, just writing the value for contraction. It is simply which is equal to V2 square by 2G. Okay. So next, what about this one? HF2 plus certain enlargement I am going for. Therefore, this value will be equal to V2 minus V3 divided by 2G I can say. Okay. So plus this value will be equal to HF3. Okay. So HF3 plus exit. I am writing this value of exit is equal to V3 squared divided by 2G is the exit here. Okay, this is a relation, this is a step for the total loss of head or the difference between the reservoir levels here. Okay, therefore, if you observe carefully, H value is known. What is the value of H, which is equal to 18? It is given. So we have in terms of V1. So HFN will be equal to 4FLV square by 2GD, 4FLV 2G, 4FLV 2GD. But we have to convert the values of V1, V2 and V3. We have to substitute only one relation. Therefore, get the relationship between V1 and V2. And get the relationship between V1 and V3. Substitute all the values in terms of V1. Okay. Therefore, I am writing the values in terms of all the relations. So try to get the relationship between V1, V2 and V3. Therefore, I can write here, yeah, A1 V1 is equal to A2 into V2. And again I can write A1 V1 is equal to A3 into V3. I am equating these two and I am equating these two here to determine the relations. Therefore, we can get pi by 4 into D1 square into V1 is equal to pi by 4 into D square into V2 I can write. Okay, so you'll be getting some value of V1 in terms of V2 you can get. Okay, therefore I'm writing this value as pi by 4 into D1 square into V1 is equal to pi by 4 D3 square into V3 I can write. Therefore, we can get the relationship between V1 is equal to some value into V3 I can get. We can get these two relations. Now substitute these two relations in this entire statement. I will write the statement for you. Okay, 2 minutes. Okay, so H is equal to 0.5 V1 square by 2G plus HF1 is nothing but 4 F1 L1 V1 square divided by 2G D1 plus V2 square by 2G plus what is the head loss of friction in the second pipe? So I can write this value as 4 F2 L2 V2 square divided by 2G into D2 plus I can write this relation as V2 minus V3 whole square divided by 2G plus 4 F3 L3 V3 square divided by 2G D3 plus V3 square divided by 2G. This is the value here. Okay. So if you go on substituting all the values, so substitute the value of V1 in terms of V2, substitute the value of V1 in terms of V3. If you go on substituting all the values, so you will be getting some value outside. So you will be getting after calculating all the relations, so you will be getting V1 is equal to 1.166 meters per second is your velocity. Or doing all the calculations is the value of velocity here. So after doing this one, you can use the relation Q is equal to A1 V1 which is equal to A1 V1 which is equal to pi by 4 into D1 square. So 0.3 whole square into what is the value of V1? I can say the value of V1 is equal to, I am removing these terms for you. Okay, so 0.3 whole square into V1. I can get the value of V1 is equal to 1.66. 1.166 is the value here. So the value of Q is equal to, final value is equal to 0.082 meter cube per second is the discharge that is flowing in the given pipeline. Okay, so this is your final answer. Please note down. And we have one more case. We have to do the same problem by neglecting the minor loss. And neglecting the minor loss in the sense, you will be getting only the losses due to friction. That means we have to include this term 1, term 2, term. You have to use these three terms here to determine the value. Please note down. Okay. Right. Okay. So let us go for the next case we have in the problem. So neglecting the major losses, minor loss in the sense we have to go for the inclusion of only the minor losses HF1 plus HF2 plus HF3. Therefore we will be getting 4 F1 L1 V1 square divided by 2G D1 plus 4 F2 L2 V2 square divided by 2Z into D2. So plus I can say 4 F3 L3 V3 square divided by 2G33. So this is called as something like major losses, okay, which is due to mainly friction. So after getting all these things, so in this case the value of V1, is equal to, after substitute the value of V1 in terms of V2 and V2 in terms of V1 and V3 in terms of V1. So you will get the value here because height is given as 18 meters, it is given. Height is given as 18 meters. Okay, therefore I am substituting the value of 18 meters here. So F1, F2, F3 values are also given for us. So after substituting all the values, you will be getting the value of V1 is equal to, I can get the value of V1 is equal to 1.18 meters per second is the value here. Okay, and along with that, the discharge. Okay, you can get Q is equal to A1 into V1. So pi by 4 into D1 square into V1. So pi by 4 into, what is the value of D1? Diameter of the pipe 1 is equal to, the first diameter is 300 mm. So 300 mm in the sense I can write this value as 0.3 square into V1. It is equal to 1.18. Therefore the discharge in this case, the final value without considering the minor losses, the discharge is equal to 0.0834 meter cube per second is the value here. And if you observe what is the discharge in the previous case? Discharge in the previous case is equal to 0.08, 0.08. The only discharge will be always constant. Okay? But the velocity changes. In the previous case the velocity is 1.16. Considering the minor losses. So without considering the minor losses, if you consider only major losses, the value is 1.18. The velocity is increased here. There the velocity is 1.16. Here the velocity is 1.18. So try to observe all these differences. It will be very, very useful for you in the examination. Please note down. Next we have to go for equivalent pipe. Okay. I am going for the equivalent pipe. Equivalent pipe. First of all, let me define the definition of the equivalent pipe, then I will explain clearly. Equivalent pipe is defined as a pipe of uniform diameter having loss of head and discharge equal to the loss of head and discharge of a compound pipe consisting of several pipes of different lengths and diameters. The uniform diameters of the equivalent pipe is known as the equivalent diameter of the series or the compound pipe here. I will draw the figure for it, then you can understand clearly. Now for example, I am taking a pipeline which is having the variation in the diameter in this way. It's having the diameter in this way here. Okay. Yes. Okay. Now for example, it is having a diameter of D1 and is having a length of L1. I am just choosing an example of series in pipes in series or compound pipe here, and I am taking this length of the pipeline is equal to L2, and I am taking this length of the pipeline is equal to L3, and this diameter is equal to D2, and this diameter is equal to D3 I am saying here. So D1, D2, D3, L1, L2, L3, V1, V2, V3. Now what I want to do is, whatever the discharge that is coming out from this pipeline, let the discharge that is coming out from this pipeline is equal to Q. Is equal to Q. Okay? The same discharge should be made from one more pipe. Okay? That pipe is called as an equivalent pipe, such that that pipe should have the same diameter, should have the same uniform cross section. It should be made up of the constant pipe here. Now see here, I am just drawing a pipeline here for you. Okay. Okay. And this is having a diameter of D1, having a velocity of V here, and is having a length of L. Okay, and it is having the same discharge Q. I am removing this velocity and placing the discharge Q here. Okay, and it is having the loss of friction HF here. Okay, and this total loss of friction is nothing but HF1 plus HF2 plus HF3. So the total loss of head is equal to, in the given pipeline, the value will be equal to HF1 plus HF2 plus HF3 is the value. It is the total loss of head due to friction. It is the total loss of head due to friction here. Okay? In the given pipeline. In the given pipeline is the total of head, loss of head due to friction. Now, what I want to do is, this is the pipe which is in series, which is having different diameters for different lengths here. Okay? Now, I want to make a pipe, I want to manufacture a pipe which is having some diameter D, such that it should produce the same discharge as that of this pipe. The discharge should be constant, should have the same discharge as that of the first pipe, which is the compound pipe, and it should have the same loss of head here. Whatever the loss of head that is produced in this pipeline should be same with the loss of head that is produced by these three number of sections. The total loss of head in this section, in this pipe, will be equal to loss of head by section 1 plus section 2 plus section 3. This total loss of head, let it be some value HF1 and let it be some value HF dash and let it be some value HF double dash, and this value should be always equal. Of this HF dash we should be equal to this HF double dash. That is the relation here. There is a relation here. Okay. So the loss of head in the compound pipe will be equal to loss of head in the same diameter. Therefore, this pipe is called as the equivalent pipe. Is also called as the equivalent pipe. This equivalent pipe which is having some diameter D. Okay. So what is the purpose of this equivalent pipe? Actually, what will be happening is, due to the presence of this contraction, see we have contraction, see we have sudden enlargement, sudden contraction, we have sudden enlargement here. Due to sudden contraction, sudden enlargement, what will be happening is, there is some more amount of energy loss. There is more amount of huge amount of energy loss there here. So to recover this energy loss, we can do one thing. Okay, so therefore we can provide a pipeline, okay, of same diameter. And one more thing is, manufacturing of this pipe is somewhat complex. Manufacturing of this pipe is somewhat easy compared to this pipe here. Manufacturing of this pipe is easy compared to the manufacturing of this pipe here, because it is having many number of sharp corners and all those things. Okay, so whatever it may be, it is the cost effective. It is the cost effective. It is the economic point of view here. We can reduce the noise also here. So this type of pipe is called as the equivalent pipe. I will define the definition once again. Equivalent pipe is a pipe which is having the uniform diameter, discharging some value Q, and the value of loss of head HF such that the loss of head is equal to the sum of the loss of heads of the three sections in the given pipeline. It is defined as a pipe of uniform diameter having the loss of head and discharge equal to the loss of head and discharge of a compound pipe consisting of several pipe of different lengths and diameters. The uniform diameter of the equivalent pipe is known as the equivalent diameter of the series or the compound line, and this diameter is called as the equivalent diameter. This is called as the equivalent diameter. Okay, so D is called the equivalent diameter. So we will be asking, determine the equivalent diameter of the pipe. In that way we will be asking. Now I want to write some relations for you. Okay, now what I can say, this total head loss. The total head loss is equal to total loss I can write. Therefore I can get the relation is equal to, for example, if you are connecting this pipe to the if you are connecting this pipe between two number of reservoirs, therefore I can write this value as level between the difference between the levels in the reservoir is equal to, I can write this one as HF1 plus HF2 plus HF3. Let us consider this one, or you can write this one as plus so on. As many number of pipes, you will be getting as many number of terms of HF3 here. HF, right? So okay, I can write this value H is equal to, I can write the value of H is equal to simply 4F1 L1 V1 square by 2 into ZD1. So 4F2 L2, so V2 square by 2 into ZD2. Okay, so 4F3 L3 V3 square divided by 2 into G into D3 is the value here. This is the relation here. Okay. Now in this relation what we will be doing is, I will be substituting the value of discharge Q. I will be calculating the value of discharge Q for you. So discharge Q is nothing but I can write, Q is equal to A1 into V1. So A1 stands for pi by 4 D square into V1. Therefore I can write V1 is equal to Q divided by pi by 4 into D1 square I can write. So therefore in the same way I can write the value of V2 is equal to pi divided by Q divided by pi by 4 into D2 square, and V3 is equal to Q divided by pi by 4 into D3 square I can write. D square is the value, right? So therefore I can write this value as H is equal to 4F1 L1 into, so what is the value of V1 square? I can write the value of V1 square is equal to Q square divided by pi by 4 by D1 square whole square. I am writing this value. So Q square, so or you can write Q divided by pi by 4 into D1 square whole square divided by 2Z into D1, plus I can write this value as 4F2 into L2. So Q2 divided by D square pi by 4 D2 square whole square divided by the value of 2Z into D2, and I can write this value as 4 L3 into Q divided by pi by 4 into D3 square divided by 2Z into D3. Okay. So therefore, so if you go for all these things, I am getting relation for you. So I will write a small relation for you. H is equal to, I can write this one as 4 into 16 4 So 4 into 16 into F into Q square divided by pi square into 2G into of, I can write L1 by D1 power 5, L2 divided by D2 power 5, and I can write this value as L3 D3 power 5 here. Okay, that is the value we can get from the relation. This is the relation I wrote for the compound pipe. Now for example, let us write the relationship. Let us write the relationship for the what we can say equivalent pipe. So for equivalent pipe, the relation will be equal to, for example, if you take a pipe which is having the same diameter throughout the section and which is having the head loss of HL and which is having a discharge of Q, for example. Therefore, for that pipe, we can write the relation H is equal to 4 into 16 by pi square into 2G into L by D power 5, I can write. Okay. So as I told that since H is the difference between two reservoir levels, so I am taking this tank here. Okay. So it is connected with the help of so one more reservoir tank here. So the tank is this tank here. Okay. So if this is the pipeline actually, pipe, so enlargement, and see we have one more contraction here, and we are just connecting with the help of a pipeline, right? So this is the pipe in series. This is the pipe which is nothing but equivalent pipe here. So whatever it may be, the height should be constant. The height is the difference between the levels of the tank is always equal to constant, which is equal to H I am writing. The value is equal to height H. The value is equal to height H we can write. Therefore these two values will be equal. Now I will be equating this value and this value here. So if you equate these two values, definitely, yes, you can cancel these two terms. So we are left out with only one term here. So Q square it is. If you cancel these two terms, the final relationship you will be getting, will be equal to, so L by D power 5 is equal to L1 by D1 power 5, which is equal to L2 by D2 power 5, which is equal to L3 by D3 power 5 plus so on. It depends upon the number of pipe sections we have. L1 by D power 5 is equal to L2 by D1 power 5. So plus L2 by D2 power 5 plus L3 by D3 power 5 plus so on. This is the equation. This equation, first of all, note down. This is the final equation we are getting here. So first of all, note down this equation. This is a very important equation. So definitely you may get a bit from this area. Definitely you will be getting a bit in the gate examination, minimum for 1 mark. Please note down. Okay, we'll write the list once again for you. Okay, the equation is L by D power 5 is equal to L1 by D1 power 5 is equal to L2 by D2 power 5 divided by L3 by D3 power 5 plus so on. This relation is called as, this equation is called as Dupit's equation. Very important equation it is to determine the diameter of the equivalent pipe. Equivalent, it is not equal. Equal is different from equivalent. Equivalent in the sense it is having the same effect which is produced by the compound pipe. Equal is nothing but everything is same, everything is parallel we can get here. Okay, so where L is nothing but length of the equivalent pipe, D is nothing but diameter of the equivalent pipe, L1, L2, L3 are the lengths. So number of lengths, you may have the two sections, you may have the single section in the given series of pipes. So D1, D2, D3 are the diameters of the corresponding sections we have. Okay, so please note down, we have to go for a simple problem in case of this Dupit's equation. Okay, should do a small problem in that. Right. Now the problem is a piping system. A piping system is nothing but duct system. Duct is nothing but a piping system. Consists of three pipes arranged in series. The length of the pipes are 1200. It is given in the previous question paper. Okay. The length of the pipes are 1200 meters, 750 meters, and 600 meters. And diameters are 750 mm, 600 mm and 450 mm respectively. The first question was asking, transform the system to an equivalent 450 mm diameter pipe. Okay. Next. Second one, determine the equivalent pipe diameter for the pipe of 2550 meter long. First of all, let me draw the figure which is given for this. Figure is not given for us. First of all, let me write the given data on board. Okay. So this problem, the value, the three pipes, the piping system consists of three number of pipe series in series. The first diameter, the first length is equal to, the first length is equal to 1200 meters. The second length is equal to 750 meters. And the third length is equal to, I can write this one as 600 meters. Okay. And he was just telling the diameters. So D1 is equal to 750 mm. So D2 is equal to 650 mm. And I am writing the value of D3. D3 is equal to 450 was telling. There is a value here. Now we have to determine, the first question is, first of all let me draw the figure by using this arrangement. See 750, it is actually reducing diameter thing here. So I am reducing the diameter. Again we are reducing the diameter here. You can observe the difference. Okay. Okay. So the length is the length. Okay. L1, L2 and then L3. Diameter D1, diameter D2 and diameter D3. So what we have to calculate here? We have to calculate the diameter and length of the equivalent pipeline. So D1, D2 and then D3 are the values. Okay. Now see here. The first question is transform the system, transform the entire pipeline to an equivalent 450 mm diameter pipeline. Okay. So I should get the equivalent pipe of diameter is equal to 450 mm. Okay, so what the length should be. So what I want to do is, I want to make this total pipe, into a pipe of constant diameter D. The diameter should be equal to 450 mm. I can write this smallly also, whatever it may be. I want to make this pipe into the form of constant diameter. The diameter should be 450 mm. Then what should be the length of this pipe, or to how much length we have to manufacture this pipe here. Okay, such that the loss of head in that pipe should be equal to loss of head in this pipe. Depending upon that equality only, we have wrote this relation, that is nothing but L by D power 5 is equal to L1 by D1 power 5. Okay, is plus L2 divided by D2 power 5 divided by L3 by D3 power 5. I can write. This is a relation here. A very important relation. Since we have 3 lengths and 3 diameters here. Therefore, I can write what is the value of L. I am substituting all the values in relation. L is to be determined. D1 is equal to, convert into meters. D1 is equal to, I am writing 0.45 whole power 5 it is. It is whole power 5, not whole power 3. Should be very careful regarding this power. Okay. So whole power 5 is equal to, so L divided by what is the value of D is equal to 0.45 whole power 5 is equal to, what is the value of L1? You will be getting 0.12 divided by, what is the value of D1? Is nothing but 0.75 whole power 5. So what is the value of L2? 0.75 divided by, what is the value of D2 stands for 0.62 whole power 5. Okay. So plus, what is the value of L3? L3. So L3 is equal to 0.6 whole cube, not whole cube, divided by, we can get the values. D3 is equal to how much? 0.45 whole power 5. It is the value. Okay. Now after substituting all these values, the final value of L is equal to, the diameter of the final value will be equal to 0. So the length you have to calculate now. The length is equal to 8713 meters. The length is equal to 8713 meters is the value. This is the final value. Okay. So this is the length of the equivalent pipe. This is the length of the equivalent pipe here. So we have to manufacture. That means in order to get the same effect. So whatever the discharge this pipe is having, whatever the head loss this pipe is having. Okay. So this pipe should have the same discharge and same loss of head. So for that we have to manufacture a pipe of diameter D of length is equal to 8713. What is the length of this one? You can observe here. If you add these three things, so 1200 plus 750 is equal to 1950. 1950 plus 600 is equal to, you will be getting 2500 is the value. 2550. Here see the value. Here the value is 2500 approximately. If you add all these lengths, here the length is 8713. Approximately this length will be 3 times the value of the compound pipe length, or length of the compound pipe, or the pipe length which is in series we can get. Okay, please note down. And we have one more case to do. Please note down. Okay. Let's do a small, let's go for the next case. We have the second case. The second case is, in this case, we have to determine the equivalent diameter of the pipe. We have to determine the equivalent diameter of the pipe such that the length of the equivalent pipe is given for us. The length is equal to 2550. The value is equal to 2500 here. You can get the same relation. So, we need to write the values once again. The length is equal to 2550 meters is the value. Okay. Therefore, by using the relation, so L by D power 5, so L1 by D1 power 5, so L2 by D2 power 5 plus L3 by D3 power 5 is the value here. Okay. So, all these values are known to us. Now L2 is known. Therefore, determine the value of D. We have to go for the fifth root. Okay. So, try to be careful with your calculators. So, you have to go for the power of 1 by 5. Okay. So, after calculating this, after substituting this value will be equal to 0.5578 meters is the value here. That is the diameter. So, if you convert into meters, let us mm, you will be getting 557.8 mm is the value here. That is the value. It is the diameter of the pipeline or the equivalent pipe that we have to maintain in order to produce the same discharge or the same loss of head which is produced by the compound pipe or the pipe in series. There is a concept regarding equivalent pipe here. Okay. So the last topic from the pipes in series, not pipes in series, flow through pipes. The last topic from the flow through pipes is pipes in parallel. Let us go for the pipes in parallel. Very important case. In the previous case, we have seen the pipes in series. After that, we have seen the equivalent pipe. Now we have to go for the pipes in parallel here. Okay. Right. So I want to just go for a simple figure for you, then you can understand clearly. Pipes in parallel. Okay. You can see okay. You can see the arrangement for the system. Okay. For example, this is the pipe, this is the initial pipe through which water is flowing here. Let Q be the discharge of the liquid that is flowing in this pipeline here. And since we have some obstruction, something like obstruction, this is used for dividing the liquid flow rate into two pipe sections here which are parallel to each other. Okay, and certain amount of liquid, this total amount of liquid, certain amount of liquid will be entering into this pipe 1 here, and certain amount of liquid will be entering into this pipe 2 here. So this is having the same length L1 and then L2 here. So Q1 and then Q2 are the discharges. So at the time of leaving, again the discharge will be equal to Q here. So Q is always equal to Q1 plus Q2. The very important condition in the parallel is nothing but, so if you place the arrangement in this way, the loss of head in the first pipe is equal to the loss of head in the pipe 2. For example, HF1 stands for loss of head in the pipe 1, HF2 stands for loss of head in the pipe 2. Whenever if you have the parallel arrangement, these two pipes are parallel in arrangement. So therefore the loss of head in the first pipe will be equal to loss of head in the second pipe. This is the arrangement here. In the first pipe will be equal to loss of head in the second pipe. Okay. So this is the arrangement. So in case of series, discharge at every pipe section is constant. But in case of parallel, discharge at every section cannot be constant because the flow got divided here. The flow got divided. Therefore, the discharge at this section will be different if I decide this section here. So what about this one? Yeah. So whenever if you across the pipelines here, definitely you will be having the arrangement such that the HF1 should be equal to HF2 here. This is a very important condition you have to remember. Okay. So therefore I can write this value as, so 4 F1 L1 V1 square divided by 2Z D1 is equal to 4 F2 L2 into V2 square by 2G G2. 2G D2 is the value here, right? Okay, so let us do a small problem in this case here. So I am writing this value as Q1, I am writing this value as Q2 here. Yes, let us go for the problem. Just note down this one, please. We have to. It's a very important case. By using this condition only, we can determine the unknowns. Okay, you may have different number of, we have number of arrangements. You may get any type of arrangement. You may get a bit from series and parallel. Series or parallel, you may get either one bit. You will be getting only one bit from either series or parallel. And you will be getting one more bit from the previous conditions, the different losses and all those things, Darcy, V-swatch, and you may expect 2 marks for 2 bits from this concept, flow through pipes. Okay, now see here. So this is a problem that is given for us. So the length of 2 pipes which are in parallel or which are parallel to each other, length of 2 pipes is given as 1000 mm. Okay, let us take this figure only. This is having a length of L1, this is having a length of L2. Therefore I am taking L1 is equal to L2 is equal to 1000, I can say 1000 meters it is. Okay. The diameters are unequal. Okay. See the diameters, for example, these diameters are equal, for example. If these two values are equal, then the same discharges will be flowing. Therefore, Q1 will be equal to Q2. The same discharge will be moving along these pipelines here. If the values of D1 is equal to D2, D1 is equal to D2 here, then discharge Q1 will be also equal to Q2. It depends on the diameter values. If the values of diameters are unequal, then the values of discharge will be also unequal there. Okay. So therefore I can write this value as D1 is equal to, it is given 0.8 meters, and I can write D2, and I can write the value of D2 is equal to 0.6 meters. Okay. And the friction factor is same for all the pipes. So F1 is equal to, F2 is equal to, it is given 0.05 it is given, and the discharge, the total discharge is given as 2 meter cube per second. So we have to determine the discharges Q1 comma Q2 is equal to how much. So what is the discharge flowing in this pipeline? What is the discharge that is flowing in the pipeline? This is the parallel pipe arrangement. This is the parallel pipe arrangement here. Parallel pipe arrangement here. So certain amount, whenever for example 100 liters of liquid is flowing per second, so some 80 and 20 will be entering into this region. So what is the proportion in which the liquids are being divided, in which the total discharge is being divided, we have to calculate. So we have a relation which is nothing but HF1 is equal to HF2. There is no other relation for other than that. There is no other relation other than the condition HF1 is equal to HF2. Therefore, if you see in the examination, if you see the arrangement in the parallel, if 2 pipes are seen parallel to each other, just remember one point. If these 2 pipes are parallel to each other, or if any 2 pipes are parallel to each other, you have to equate the loss of head in the pipe 1 to the loss of head in the pipe 2. Therefore, I am writing this value as simply, yes, HF1 is equal to HF2, I am writing here. So what is the value of HF1? So 4F1 L1 V1 square divided by 2Z D1 is equal to 4F2 L2 into V2 square by 2G into D2. And if you observe carefully, since L1 is equal to L2, I think we can cancel these two terms, right? And it is given F1 is also equal to F2 here, the coefficient of friction. Therefore, we can cancel F1 and then F2. So we can cancel 4, we can cancel 2G and 2G. So what is the relation we have here? So we are left with only the relation V1 square by D1 square is equal to, I can write this value as V2 square by D2. We can form the relationship between V1 D1 and V2 D2 also. Okay. Diameters are given, D2 D1 values are given. What about the velocity? Discharge is given. So therefore I can write, so discharge is equal to A1 V1 is equal to A2 into V2. Yes, we have a relationship here. Therefore I can write this value as pi by 4 into D1 square into V1 is equal to pi by 4 into D2 square into V2 I can write. Therefore pi by 4 will be cancelled. What is the diameter? So 0.8 whole square into V1 is equal to 0.6 whole square into the value V2 I can write. Right? So you will be getting the relationship between V1 and V2 is equal to, I can write V1 is equal to 1.15 into V2 I can write here. V1 is equal to 1.15 into V2. That is the relation. Now substitute the value here. So I am writing this relation as, I am doing this one. Okay. So V1 is equal to 1.15 V2 whole square. Okay. Is equal to V2 square divided by D1 how much? D1 is equal to 0.8. Okay. Divided by D2 how much? D2 is equal to how much? We are getting the value is equal to 0.6. Okay. So after doing all the calculations, the value of V2 is equal to, so value of V2, I don't have the value of V2 here, no problem. So after getting all this relation, you will be getting the value of V2 here. So after calculating the value of V2, we have the relationship between this one here. So after getting the value of V2, determine the value of Q is equal to A2 into V2. That value is equal to 0.658 meter cube per second. Can write 0.658 meter cube per second is the value here, right? Okay. Next, in the same way, you can determine the value. This is Q2, this is Q1, and we can write the value as Q is equal to A1, V1 is equal to, that value is equal to 1.342 meter cube per second is the value. So this is the concept of flow through pipes. Okay. So first note down. I will go with the conclusion for you. Just note down. This is A1 here. Please note down. Okay. So important point that we have to remember in case of the pipes in parallel is nothing but we have to remember the point is the loss of head due to friction always remains constant in all the parallel pipes. That's all. That is the main important conclusion. So this completes the flow through the pipes. in your syllabus, in the GATE syllabus. Okay, so you may expect 2 marks from this topic or 1 mark from the entire topic we have. The only thing is you have to see about the formulas in case of minor loss and major. Major loss means it is having only one formula, 4FLV square by 2GD. And the second thing is you have to go for minor losses, exit, entrance, contraction, enlargement, obstruction, and the pipe bend fittings. Okay, and one more important point is the difference between the levels of the reservoir is always equal to the total loss of head that is occurring in the pipe which is connecting the reservoirs here. That is very important point here. Okay, so we shall continue the next topic in the next class. Okay, thank you.